Hello and good evening, everybody. Welcome to session 4 in Leaving Cert Physics. This is electricity 4. Today we're looking at current, voltage and resistance. By now we're seeing that a number of the titles are kind of overlapping. So there's a lot of that in electricity. It's a very repetitive and building on itself kind of section. It's a long section. A very long section. You could have, depending on your book, you could have the guts of 10 chapters on this, whereas you might have 1 or 2 on previous sections. So there's a lot to electricity and a lot of repeating terms. So we're going to be looking at voltage today, and we first looked at voltage in session 2. You know, we first looked at it in session 2, and we talked about it really as a potential difference. We talked about it in a very kind of almost Puritan way. And we talked about it as a difference of potential energies in a force field, you know, due to its position in a force field. Today we're going to again look at it, but really today it's going to be within a circuit. You know, we're going to be looking at current, voltage, and resistance within circuits. So it's good to know that there's different ways to look at it, but it is always the same thing. So that when we say voltage, it is just that potential difference. When we say the voltage of a circuit, we're talking about the potential difference from one end of the circuit, let's say one end of the battery that's connected into that circuit, to the other end of that circuit, which will be the other end of that battery. So that's what we're looking at today. So voltage, we were very technical in our definition. And we said it was between 2 points, which is still the same in a circuit. Now, before I get ahead of myself, I just want to make sure that everybody's logged in and okay. But I think by now things are generally working for people. We had an issue a couple of weeks ago with the screencasting, but I think that's working fine now. So I think I'm good to start, and so I shall. All right, this is electricity. This is session 4. And we are looking at, we're looking at current, voltage, resistance. So what are we looking at here? Well, here's what our curriculum guidelines tell us. We need to know about electric current. We need to know what it is. We need to be able to describe it in its basic form. We have loads of values here. We have loads of units, loads to make sure that we're feeling good on. Sources of EMF. Now, EMF was electromotive force. It was yet another way to describe voltage. So an EMF could be described as a third way to describe it. An EMF would really be when we're applying that voltage or when we're applying that potential difference to a circuit. We need to talk about where that comes from. And then lastly today we want to look at conduction. Now, there's lots of ways to look at this. We're going to start by building our circuits, and we're going to talk about the things that affect how that circuit runs. So we're going to look at conductions in various substances. Now, this involves some V versus I graphs that we mightn't get around to today, but it might come a little bit later, but it is still under this umbrella of electric current. Okay, as a brief recap on last week, it's very, very important to know. So whether you're watching this live or whether you're watching it back, it's very important to know a potential difference, also known as voltage. It was 2 weeks ago that we did it, but it is very important to know because, as I said at the start, this week we're looking at it in terms of applying it to a circuit. So we need to be okay with saying, okay, it's a 9-volt battery. And what does that mean? Well, that means that between the potential difference between this point here and this point here, the potential difference there is 9 volts. And so if I go and connect a circuit through there, the potential difference between that point, shouldn't have used the same color pen, but between that point and that point is also 9 volts. And so the voltage as applied to the circuit will be 9 volts. So it's important that we're strong on that going into this. Now we'll go easy on it to start. We're going to look at that question that we brought up at the very end of the last section. I'm also going to talk a little bit at the start just about planning, because we're going into the midterm break. So I know someone was asking me about getting organized and kind of like the levels of work that are expected of you at this stage of the year. Some students are thinking, I don't really have to start yet. Some students are thinking, I'm already working too hard. Am I going to burn out? Do I need to think about things like pacing myself? Some students are thinking, I'm getting too much homework to do anyway. I don't have time for study. Some students are looking at their house exams, which should probably be your last set of house exams. So we're going to talk about that a little bit at the start, and obviously through the lens of physics. And then once we've that done and the question corrected, we're going to get into current, voltage, and resistance. We're going to start talking about resistance today for the first time. Okay, balancing work, and I've put a number there, 240. The exact timetable hasn't been released yet, but you are roughly 240 days away from your Leaving Cert Physics exam. Okay, which is a very big number and also a very small number. It's a big number because 240 is a big number. It's a big number of days. If you were to do 1 hour a day of physics revision, that'd be 240. You're not going to do 1 hour a day of physics from now until the exams, so you're not going to get 240. If, however, you averaged 20 minutes, then that would be 80 hours. Now, that's where it gets interesting. Those numbers get interesting because 80 hours is certainly enough to revise a course. Certainly enough. You would have done almost 200 hours of physics across the 2 years. So you might say 80 hours isn't enough, but if you do it well, it's enough. But then if you're only averaging maybe 10 minutes per day, that's only 40 hours. Now, I would say that's too little. Now, I'm not counting, by the way, doing these 1 hour sessions. I'm talking about pure, and I'm not talking about your homework. I'm talking about pure study. So 240, it's a nice, that's kind of why I left it at 240, because it's a really nice number to work with in terms of calculating kind of how many full hours you'd be doing. As you go to the end of the school year, and as you go into the Easter break or May or something like that, you'll be thinking, oh, sure, I'll be doing way more than that. And you will to a certain extent, but you're only really going to get maybe 10 to 20 days there where you're free to do, let's say, maximum 1 hour per subject. Now, that's being very optimistic. So that whole leaving things until the end of the school year, it works for some people, but it doesn't for most. So balancing work is important. I can't tell you exactly, which of these two is the way to go for you, because it all depends. You might be getting huge homework each night, or you might be getting very small homework each night. You might be getting a weekly class test or something like that in half of your subjects. It's totally different depending on the student, depending on the teachers, depending on the school, depending on the subject. It's totally different. All right. So what you count as study and what you don't count as study is up to you. But I would go back and I would just have a moment to think this evening about roughly 240 days. All right. And so multiply that by, whatever, 10 minutes, 20 minutes, whatever you're going to get on average. So if you're not going to study physics tomorrow or Saturday or Sunday, which I would expect is probably the case for a lot of people, if you were not doing that for those 3 days, you would need to do an extra 40 minutes today. You need to do 40 minutes to average 10 minutes across those 4 days. So 10 minutes sounds like nothing, but 10 minutes is 1 hour 10 per week, which again is very, very manageable. But every day you don't do anything, it really puts a lot of pressure on that figure. So totally up to you. You have loads of time if you do it now. In terms of the midterm break, what would I recommend there? Again, it depends kind of on what way your exams are. Some people, I know some schools I was talking to have been doing their exams this week. Some are doing it the first week they come back, or the second or the third. So your midterm break will probably be decided a lot by that. If you've been working really hard the last 2 weeks and your exams were this week, yeah, absolutely, take most of it off. If your exams are the week you come back, you're going to be working naturally through the break. If your exams are the week after you come back, you'd be tempted to give yourself a full week off, but I wouldn't. There's 9 days. There's 9 days in your midterm break. You've got the 2 Saturday, Sundays, and then you've got the 5 weekdays. I would be expecting a serious student to be looking at probably 4 of those days in terms of proper study. And even if it's not monumental 10 hours a day kind of study, even if it was as simple as, okay, I have sorted out all my notes in all my subjects, I have sourced my exam papers, I'm prepped and ready for the next term, I did 1 mock paper in each of the subjects, and now I know, okay, in physics I'm flying with my electricity now, but I hadn't a clue about temperature. I forgot everything we ever did. It was during the lockdown, it was the online learning, I never really knew it in the first place. That's a thing that I'm going to have to spend extra time on. So if you took this next week as a research week, I think that would be time very well spent, because to be honest, you don't have time to do this later in the year. Once you get back from your midterm break and you've done your November exams or whatever they are, and you're coming up to Christmas, you're just going to be hearing about the mocks. It's just going to be mocks. And you're going to be like, oh yeah, grand, it's fine. It's not till February, blah, blah, blah. And then you go off on your Christmas break and you will be doing some study over Christmas break. You'll come back and the mocks are just going to hit you. It's going to feel like days. It'll be weeks, but it'll feel like days till the mocks hit you. And then once the mocks start, I mean, that's just it. I mean, then it's just orals, orals, interviews for this, prepping that, submitting this project, depending on your subject. So like, it gets mad busy. So you might be feeling like this midterm break is the time to take a bit of time to relax. And yeah, it is for a few days, no problem. But this is the time to get your research work done. Because once you hit into Christmas time, it all starts going at 90. But that's totally your own call to make, everybody. All right, so let's look at this question that we looked at last week. We looked at it in terms of how to approach it or how to evaluate it. In terms of picking this question, we have great choice in the physics paper. And this year in the exams, you will have that extra choice again. So that's nice to have. So there's less pressure on you to pick any particular question. Just because you have extra choice. However, there's still just as much choice, just as much pressure to choose a particular question based on the marks. Now, what do I mean by that? Very, very briefly. $56 marks. A question that has 56 marks. If we're a H1 person, that's 90+%. Which means that we need to be getting, out of a 56 mark question, we need to be getting, on average, 50.4 marks. So of course we're looking at 51 marks per question. And as such, If within this question, there is a 6-mark question that you know it is impossible for you to get, then you are now fighting out of 50 marks. And the H1 is gone for that question. Now, that's a little bit extreme, of course, and you can always make up for it in other questions, but the higher up you're aiming, the less leeway you have. Because if you got, let's say, we're aiming at getting 51 marks per thing. If you got 45 marks in one question, which is actually pretty good, you couldn't even make up for it in the next question. If you got 45 and 46 and 56, you'd still have to get a 52 in the next question to bring you up to that average across these three. Okay, so there is leeway, but the higher up you're aiming, it's less and less. So the students who are looking to get the H1, just taking those to start with, they should be looking at each question and not assuming, but looking at, are the full 56 available to me? What is ruled out? Now, there'll be very few questions that can be ruled out, that you can't give some kind of go. Definitions should be a given for everybody. Now, describe an experiment is one that if you haven't seen it, you're taking a chance there. That's 12 full marks. Calculations there were the next 12 marks. We talked about those. Those marks are very, very generous. Calculating new capacitance, so it's another calculation question. State two differences between a capacitor and a battery. A H1 student knows that answer. A H3 student knows that answer. Touchscreens contain two polarizing filters. Well, that was a bit of a recap on light. We said that last week. And give one application of capacitors other than touchscreens. So you would be able to come up with something there if you hadn't. So a H1 student would really, really like that question, unless they were totally unfamiliar with this. And if they were totally unfamiliar with this, that's 12 questionable marks. You have to come up with that experiment yourself and hope that it works. And there's not a lot of leeway on that. So a H1 student, if they knew that starred question, they are beating into this question. They're loving it. If you were aiming more towards the middle, and I don't know what individual people in this class are aiming for, that's your own business. But you're going to go down roughly 10 or 5.6 marks each time. So I'll go, what I'll do is I'm going to go 5, then 6. So here you're aiming for 51, then 45, then 40, then 34, etc., etc. So the H2 person could get away with not knowing that experiment if they were going to be very strong on every other part. And the H3 and the H4 are really not worried about that experiment part at all. And in fact, could look at the rest of that question and go, hang on, do you know what? This is a very quick question. So maybe if you were a H3 or a H4 person and you generally dismiss electricity and you say, well, that's not for me. I'll do all my other parts. I like light and I like heat and I like, forces and things like that. And then you did question 8, and then all of a sudden you looked at question 8 and you go, oh my goodness, I've done that terribly. Then you might look at question 9 and go, okay, I don't know that starred question, but I can always do a definition. I'm decent on my calculations from the maths tables, giving me the formula. And you know what? Now that I look at it, those last few questions aren't that bad. And so a H3 or a H4 student could come into the likes of a question 9, ignoring the second part, even though it's 12 marks, I know it's a lot, but could really absolutely fly at those other 44 marks and do them very, very quickly compared to some other questions. So we started to look at that last week. We look at it a little bit more with each week that passes as to strategy for picking questions, because you wouldn't believe how big of a difference that makes. I have seen students who are H1 pick the wrong questions, sometimes out of rushing, sometimes out of arrogance, sometimes out of being just a bit blind to certain sections because they discriminated against this section or that section, sometimes by misreading a question. And I've seen them end up with H2s and H3s. And I have seen students overperform in exams because they were very clever at picking their questions, answering them in the right order, picking up little marks, not dropping silly marks. It's so important. And that's why I'll be talking about this in term 2, where we're going to really prepare very, very well for the mocks, and we're going to take them very seriously. Anyway, that's enough prattling on. Let's talk about the actual the answers themselves. So we had to define basically capacitance and electric field. Almost any time you see a definition in the physics exam, it's worth 6 marks. A tree and a tree and a tree and a tree. So capacitance is the ratio of charge in a capacitor to the potential difference across it. Any similar wording to that, and what you're going to get is full marks. It has to be specific in the sense of there is that clear idea of division. So ratio is just division. It needs to be clear that it is charge in an electric sense. So charge, the best way to say that is to say something like charge on a capacitor, or charge on a surface, or charge across a device, or something like that, to the potential difference across it. So to the, why? Because it was ratio. With a definition that has a formula, C equals Q over V, you can put C equals Q over V and give the correct notation. I'm not a big fan of it. I always like the word definitions. I think it just comes across much better. But again, I've said it so many times, on the right hand side, look at that. That formula is in the tables. There's literally a page on the tables, and you go halfway down it, and it will say the word capacitance, and it will say C is equal to Q over V. And that gives you the answer. A person who hates electricity, hates it, and didn't spend 1 minute revising it, should be able to do that first question and get 6 marks for capacitance. Now, they're not going to be able to do it for electric field. So I would expect literally any physics student to be able to do the definition of capacitance because of what's in the maths tables. But it does take the good student to know how to define an electric field. That's a much stickier definition. An electric field is a region of space where electrostatic forces are experienced, or forces are experienced by charged particles other than gravity. I would add there myself personally. Now, very quickly, because I do have a lot to talk about. Describe an experiment to demonstrate an electric field pattern. You knew this one or you didn't. So this is where the H1 student is not taking the chance of bluffing this one. The H3 or the H4 student who took this on as an extra question to make up for a bad question is absolutely bluffing this one, but they're answering this part of the question last. Take your quick and easy marks first. Don't start an exam with question 1, nor should you, if you are doing question 4, don't start it with part A. You don't need to answer the exam in order. The person who's marking it will figure out where your answers to what part of what question are. It'd be a good idea to label them, but don't do them in that order. Do them in the order of easiest first. In a maths exam, part A is easier than part B, so we do part A first. In a physics exam, it's not necessarily the case. I would say this is an easy one. I would say this is an easy one. I would say this is an easy one. I would not be bogging myself down in the time of coming up with an answer for this if I have a given answer ready to go on this one. Especially if question 9 was being used here to make up for another question and we were stuck for time. So this is the nitty-gritty kind of stuff. And you might think I'm doing this a little bit early, guys, but the reason that I'm doing this is that the students who are doing their preparations well, who are doing their research weeks well, and the students who are really revising and really doing the exam papers are really going back and marking their own exams and looking at a breakdown of how they did it and saying, you know what, I dumped way too much time into that experiment question, drawing this and then scribbling it out and then redrawing it and then forgetting to label it and then I spent all that time and I got 3, maybe 6 marks out of 12. And if I look down here, this was 4 marks for something that it literally took me 7 or 8 seconds to write down. when you get your CAO form or when you get your results form and it says H4 in physics, it doesn't tell you which part of which question you got right, just that you got your H4. So don't feel like you need to answer these things in an order. Anyway, zooming on ahead, that was the experiment, sorry. Calculations, fine. Okay, another calculation, fine. Differences, we should know them. Revision on light, and then a use of a defibrillator as an example of something other than a touchscreen. So the physics exam is not that bad. It always looks worse than it is. Now, I'm going to move on. Let's talk about electric currents. We've talked about potential difference. We've talked about it a good bit. We've talked about it as really looking at it in terms of a force field. But now that we've had these currents, we've had them just sitting here for ages, experiencing this force but not moving, and then placing it over here and then placing it over there and measuring this and measuring that. What we're now going to do is we're going to say, okay, this thing, it is moving. So what an electric current is, really, it's a flow of electric charge. And almost always when we say this, we're talking here about the flow of electrons. Now, that could be let me just try this up here, sorry. That could be one happy little electron going all the way from point A to point B. Or that could be another happy little electron starting at point A, moving to here, displacing another electron that moves over here, that displaces another electron that's now at point B. Either way, both of those situations are an electric current. It's a flow of charge. In our first scenario, charge is flowing from A to B. There's an electron moving there. And in our second scenario, charge is flowing from A to B. There is a movement from left to right of electric charge. So an electric current is a flow of electric charge. Now, in your diagrams, in our simulations, in the FET circuits that I'm building, it's very clearly one electron doing its loop. Sometimes it's an electron latching into an atom that just lost its electron, and it's kind of like this leapfrog knock-on effect. Either way, electric current is a flow of electric charge. It has a size, and its size, its value here is given as I, that's current. Electric current would be charge passing a particular point, and it's at a rate, so it's the rate of that. So it is the amount of charge passing a point per unit time, t. So I would equal to Q over T. That means as a follow-up, of course, by the way, that Q is equal to IT. That can come up in little questions. You've probably not done a huge amount of questions where you were doing Q equals IT, but it is there. But anyway, I is equal to Q over T. So charge is measured in coulombs times per second. So we might be tempted to say coulombs per second, which it is, but it's given its own unit, which is the amp, or the ampere. So a single unit of electric current would be 1 coulomb passing a point per second. And that's it. So electric current, that's all it is. And that should be very straightforward. Anytime you see an equation, something like the I equals Q over T or Q equals IT, you want to check the tables there. You know, we'll be talking in a moment about, you know, V equals IR and P equals I squared R and all of these kind of things. I equals Q over T or Q is equal to IT. Is that in the tables? We might assume that it is, but we should always check it, because maybe that's something that's so simple it's not there. Maybe. We'll have a look. Potential difference. Well, we knew what potential difference was. We know the potential difference is the difference in energies, difference in potential energies felt between 2 points. So there was a difference there. So delta, and we'd say potential energy. Another way to think about it was the work that was done bringing this particle from point A to point B. And so now another way of looking at voltage is to simply say it's W over Q, as in that is the work done to bring something between one point to another per unit charge. Now that's absolutely nothing new if you're very comfortable with the definition of potential difference. If you're comfortable with that idea of the kind of like the ball that you were lifting in the gravitational field, if you're comfortable with that plus charge being brought closer to the other plus charge, if you're comfortable with that difference, and I really did prattle on about it 2 weeks ago about how important it was. If you were comfortable with that as voltage, now voltage V being W over Q is absolutely fine, because it's just W, the work done, because it's a difference in energies, per charge. That's just standardizing it for each coulomb. Basically, it's the work done per coulomb, because we just defined it based on 1 coulomb, that's all. If you weren't on the ball about that definition or about the concept behind potential difference, then V is just some other letter that's going to appear everywhere and be really, really annoying. So if you've done your groundwork, you're fine. If not, you're not. Okay. Right. Let's now look at circuits. And let's look at voltages in series and in parallel. So I'm going to try and do this today, maybe if possible, without going onto the other website, because I know some people are having a bit of issues with it, but let's draw it out. We knew that a circuit, very, very roughly, would be something like this. That we'd have a battery, that we'd go in a loop, that would have maybe a bulb. Very, very rough. Okay, fine. We now know that a battery is going to have within it a voltage. And that voltage is going to be between the two ends of the battery. Now that we're connected, we now have that voltage as an EMF, an electromotive force. Electro, electric, motive, motion, and a force. So what's going to happen is the little electrons are going to go around. And so the electrons go around the circuit. As the electrons go through the bulb, there's something different about the bulb compared to the normal just wire that we were going around. There's something different about the bulb, and then what happens is the bulb is just going to heat up, and it's going to give out heat, but most importantly, it's going to give out light. It's going to use up some energy, and then the electrons are going to continue back along and into the other end of the battery, into the other terminal of the battery. So that's our basic circuit. Now there's a voltage across that circuit because of the battery, and the voltage there is between 2 points. Now imagining that the blue wire, let's say, that's going along here, imagining that we wouldn't even consider that to be a thing, it's just where it's going. We would say that that same voltage is applying across the bulb. All right. Now let's look at a voltage in a little bit more detail. Let's look at a voltage in series. Now what in series means, it means just running along the one line. So let's make our points. A, B, C, and D. Okay, between any of these 2 points, between any two of these 4 points, we would have a voltage. That's V1, V2, V3. And then we might look at this as a total voltage V. Now what I hope we're okay with is as follows, that the voltage V would be equal to V1 plus V2 plus V3. Because remember, red V there is the difference in potential energies, aka the work done in bringing a +1 coulomb from A to D, or vice versa. Well, what's V1, V2, and V3? Well, they're just parts of that journey. So V1 is A to B, V2 is B to C, and V3 is C to D. So adding up all those individual works, you will get the same as the work bringing it on its whole journey, which is A to D. And so there we go. We have that voltages in series must add up to the total voltage across those points. Again, if you understood the original basis of potential difference in voltage, it's second nature. It almost doesn't even need to be explained. If you didn't, it's a brand new thing to learn off, which is always a pain. Now, let's talk about voltages in parallel. Now, what do I mean by in parallel? What I mean is we're going to split our circuit. And so now we're going the following way, that at, let's say, this point A, we're splitting. Now, let's just call them V1, which is the voltage. I hope people are okay. Let's say from A to E, just along the middle line. I probably should have put V1 at the very, very top, but I'm sure we can understand. V2 going A, B, D, E, and V3 going A, C, F, E. Now here's the thing about that. V1, V2, and V3, as I've just defined them to you guys at home, all started at A and all finished at E. They're all between the two same points. As such, they've all got to be the exact same. So V1 must be equal to V2, must be equal to V3. It's between the same 2 points. Core part of voltages. Again, and I'm being very repetitive, but this is why it's so important. If you got the early definition of PD, you're going to be absolutely fine with V1 equals V2 equals V3. That is it. Just a little note on that. When we have our voltages, when we have let's say a circuit, let me draw up a very rough circuit here. When we have our circuit and we put in, let's say, to measure current, which we're going to be doing in a moment, and we can just put an ammeter here, that's fine. But when we're measuring voltage, of course, voltage has to be between 2 points. So voltage between here and here must be measured by a voltmeter that's in parallel. Why? Because it has to connect to 2 separate points. So it can't just be placed in the middle of everything. It has to be connected to those 2 separate points. And you can see there that the voltmeter is now in parallel. And so the voltage that it reads is the same as the voltage between those 2 points in the circuit. And so the way that the voltmeter works is itself a giveaway that voltages in parallel must be equal. Okay, so important to know. So that was voltages in series and in parallel. Okay, let's look at this little question. That's a really annoying question because it should be very, very simple. 4,000 joules of heat energy is given off when 80 coulombs passes a point in a wire. What is the PG? What is the voltage across the wire? So what we're saying is it passes a point. So we're saying overall, saying that we get 4,000 joules. And we're getting 80 C. What is the potential difference across that wire? Right. I'm literally going to mute myself for like 20 seconds. I'm conscious all the time. Mute myself for 20 seconds. And you guys at home, just have a think. You don't have to put anything in chat. Just keep it entirely to yourselves. How would you go about that question? Have a think. 20 seconds. Okay, a question like that, something like that in some way, shape or form is going to come up in the Leaving Cert, either as a short part in question 5 and you'd be raging if you couldn't get it, or as a little 6-mark question in a question, a section B question that you're doing really well and you don't want to drop these marks. What's the strategy for this? It's very, very simple. You identify what you're given and you identify what you want. Here we were given energy. Now energy, giving you an awkward one here. Sometimes that might be displayed with an E. Sometimes it might be displayed with a W. There's a few different ways we could give you energy. 80 coulombs. Well, coulombs means charge. And then it wants potential difference, which is PT, which is voltage, which is V. Now, we got to go to the maths tables and find that it says V is equal to W over Q. And if this was a 6-mark question in the Leaving Cert, you've got 3 marks for writing this. You're on 2 marks right now. That gives you your full 3. And that's how the question's done. And we're not dreaming up magic science here. We're just taking values. What do those values represent? Finding the equation, writing the equation, filling in the equation, solving the equation. And starting at 6 marks, there's 3 for the equation and 3 for the answer. On the voltages voltages in series, voltages in parallel. If I was to set up that system again and look at current, well, let's have a look. A, B, C, D. So let's look at that. I'm saying, okay, again, between those 4 points, I have, I have my currents. So that's I1, I2, I3. And then across the whole thing from A to D, I have one overall current I. Well, what could I say about this? Again, I hope this is nice and obvious. I would just be equal to I1 equals I2 equals I3. The current's got to be the same anywhere in a series. Okay, you can almost think of this like one big hose. The amount of water that passes A to B per second would have to be the same as B to C and C to D, because it's all along one line. And even if it was difficult or easy to get through that line, it's one line and it's all moving, and so it doesn't matter at what point you look at it, it would have to be the same. Where it gets a little bit trickier is now where we make our parallel. But again, it's not that bad. I kind of started with the slightly trickier one, which is voltages. Let's do our currents here. Now what I'm going to do is I'm going to establish that this is I coming in, this is I coming out. Now, obviously the same currents. To match what I did with the voltages, I'm going to describe them this way. And what I would say now is, and I'm not going to pause for a few seconds, I'm going to go straight into it, is that I'm going to say that I1 plus I2 plus I3 is equal to I. That's not to say that I1, I2, and I3 are equal to each other or anything like that. It's simply to say that there was a current going in and a current going out. Current going in, current going out. And whatever way it splits itself among those three paths, it would have the same going out as coming in. And so therefore those three currents, when added back together at that second green point, are going to have to equal a total of the current that came in and the current that was coming out. So your I there, your red I, would have to equal to the three green currents added together. Again, we didn't care about them when it came to potential difference. Didn't care. But we do care when it comes to the currents. Okay. Right. Let's see. What else do we need to have here? Just on an earlier one here, we had, and it gets easily forgotten, I suppose, but we had W equals QV. If we divide both sides by time, we get W over T is equal to Q over T by V. Now you could have said, oh, it's Q by V over T, but the over T works nicely with Q here. Energy per time gives power. Charge per time gives current. P is equal to IV. You would have talked a lot when doing electricity about P equals I squared R and Joule's law and how important that all is. Well, it's just as important to do P is equal to IV. That's very, very important. All right. More to talk about. Next thing to talk about is resistance. So the relationship between V and I, what is it? Should be pretty straightforward to start off. When we imagine, let's say, the battery in our circuit, when we increase the voltage on that battery, what we're doing is we're saying that there's a bigger difference in the potential energies between the two terminals. We've created this kind of more powerful field, if you like. And so when we connect it up and let it off and running, we would expect there to be a greater voltage. So what we would do is we would expect that as V goes up, I go up. In other words, we would expect V to be proportional to I. Or vice versa, you know, we would expect I to be proportional to V. And so as such, we would expect V to be equal to some sort of constant times I. Now, this constant here, K, isn't going to be like, 7 or something like that. What is it going to be? Well, it's going to be different for different substances. Maybe in one substance we add 5 volts, are we going to add 5 amps or something like that? It would depend on the substance. It might depend on if something's a metal or something's a plastic, or if it's in a circuit, or if it's a semiconductor, or if it's a whatever. So what could we say about K? Well, K here will clearly be equal to V over I. So what is K? K is a measure. It's the measure of the ratio. It's the ratio of voltage or change of voltage to current or change of current. So we would say that K has a high value if we don't get a lot of if we don't get a lot of increase in current. So we would say that K has a high value if we get a small increase in I as we increase V. K would have a low value if we got a large increase in I as we increase V. So that's just basic fraction work, right? And so now K seems to be about how much current we'll get compared to our voltage. As such, a high K would suggest that we're not getting a lot of current. So a high K suggests difficult for current to flow. Now we come back to our basic definitions on conductors and insulators. And so if K has a high value, it makes it difficult for the current to flow. And if it has a low value, it's very easy for the current to flow. And so now we say that K is resistance. And so R is equal to V over I. In other words, V is equal to IR. That's one of our most famous ever equations in physics. So resistance, what is it? Just like our definition for capacitance, we're talking about a ratio here. Resistance of a conductor is the ratio of the potential difference across it to the current flowing through it. So resistance is the ratio of potential difference across a conductor to the current flowing through the conductor. Again, anytime we have something new like this, we go, is it in the tables? Yes, it is. Our units here would clearly be the volt per amp, which is not the nicest. So instead what we're going to do is we're going to call it the ohm. So resistance of 1 amp would be the ratio of 1 volt per ampere. And that's resistance. When we draw a circuit, we draw a resistor, this extremely complicated shape, known by some people as a rectangle. So there's our resistor. And we simply say, okay, here there is some level of difficulty, if you like, for current to flow. All right, and we would measure it in ohms. Okay, what if we had resistors in series and resistors in parallel? So today we're going to look at our third and final thing that we measure the circuit in terms of being in series and in parallel. Oh, I never mentioned, my goodness, to my shame, I never mentioned that this is called Ohm's law. But I did mention his name here, so I got away with it. Okay, so what about if we have resistors in parallel? Let me draw a better one here. This mightn't be as easy as we first think. We have an R1, an R2, and an R3. and we've got a total R. It mightn't be that easy to think about this. Resistance is the ratio. So how does that work? Sometimes now, we didn't need to do voltages and currents, but sometimes we might like to think, okay, well, what if this was 2 ohms? What if this was 3 ohms? And what if this was 5 ohms? What would it be? You know, what's our total resistance across there? And our total now, I think it just screams out at us that it's 10. But yeah, we do need to say it. And so our resistance here is equal to R1 plus R2 plus R3. Okay, that is our total resistance. Now, the reason why would be as follows. If you look at each individual resistor, right? Each individual resistor would have, let's say R for the R1, right? It would have a voltage 1, and it would have the same current for everything. 2 would have voltage 2 and the same current, and 3 would have voltage 3 and the same current. Now I know that R is equal to V over I. All right, I know that R is equal to V over I. If we go across, I would know that V1 is equal to I R1. I would know that V2 is equal to I R2. And I would know that V3 is equal to I R3. I know that V is equal to V1 and V2 and V3. And so that is I times R1 plus R2 plus R3. But I would also know that V must be I R. And so now I have that. Okay. Last new topic for the day, I promise, and then I'll leave you with a bit to do over the break. Let's just look at resistors in parallel. So lightning fast. This one can get asked as a, not just as a formula, but as a prove this is true, which is, you know, just so nice. R1, R2, and R3, and now I've broken with my routine from earlier. Oh, great. I1, I2, I3. This one's much trickier. The formula is itself very awkward. Let's start by looking at the I's here. And let's be nice and remember that the V is V. Well, what can I say about I? I know that I1 is equal to what? It's got to be V over R. Well, it's the same voltage for all of them. And so now we're building up our currents. I also knew that I was equal to V over the overall R. And so now, if I look at combining these two, I would now have that 1 over R would equal to my 1 over R1 plus 1 over R2 plus 1 over R3. That's a horrible thing to look at fresh, but if we're comfortable with our V's and with our I's, then that R just comes from there. Okay. Now, I'd love to go into it more, but I've run out of time. I've already talked about the kind of work that you would expect to do over midterm. What I'm going to leave for you here is some Leaving Cert questions. I've left in the marking scheme for at least one of them. So this will be a PDF that'll be available in your drives later this evening or tomorrow. You could do that if you wanted to over the midterm break. Again, depends when your exams fall. And really, I'm going to talk to you in 2 weeks' time, guys. I'd like it that if by 2 weeks' time you're a little bit more organized, you know what you're doing in your notes, you've had a bit of a look at over the sections and you know where you need to concentrate going forward, and we'll keep barreling on with the electricity. All right, guys, listen, thanks a million. I hope you have a good midterm break filled with some study and some relaxation. Well earned. See you in 2 weeks' time. Bye-bye.